Hello everyone, welcome to this talk, which is called Optics for Servers. And today I would like to present a library that I've been working on based on the idea that you can implement web servers using lenses. And the goal of this library is to solve some problems that I've seen when I was working with Servant, and also to motivate the use of dependent types for software engineering. For this talk to make sense, I will have to introduce a couple of concepts first. And once we've seen all of them together, I'm going to show a demo of how the library works so that you can get a good idea of how everything comes together in a very practical sense. The first thing to answer is, what is a web server? If you Google this up, you will find pictures like this, which represent a network. In the original definition of the internet, you have different devices like a server or a laptop connected to another server or another laptop, and they themselves have an internal network connected to them. This makes it look like the infrastructure is extremely symmetric, where a laptop might connect to another laptop, or a laptop in this area might connect to another server. While this is true on the very basic implementation of networks, it is not true when you look at the way we serve web pages on the internet today. When we serve web pages, we use today the protocol HTTP. And HTTP follows a number of conventions and shows those conventions through its specification. So in the HTTP specification, you have different methods that encode different kind of actions that you can perform on the server, and you expose those operations using network requests. So at the top here, I have an example of a network request. This request uses the method get, and it points to a resource here, index.html at this path. And you have other things like the version numbers, the body, the headers, etc. The point of this example is to show that a request is merely a string that follows a format, and that the server will then ingest this data, and depending on how requests is constructed, will perform some operation. So here, because it's a GET request, it will probably return some kind of data without performing any operation. If it were a POST request or a delete or a puts, it would probably perform some kind of state. And this manifests in practice by having a client requesting data to a server. So on the left, you have a laptop, which is our client, and the laptop asks the server, can you please serve me this data, or can you please do this for me? And this operation is done through what we see here at the top, a list of endpoints that the clients can call using a different HTTP method. And so we have this asymmetric relationship now, where the client asks for things and then the server serves the resources. So here, see it responds with OK and gives a HTML file as a response. To clear up the vocabulary, this collection of endpoints that the client can call, we're going to call this the API. The single line of those is an endpoint, and the endpoint is composed as the method, as we've seen, and also a path that points to a resource that the client is interested in retrieving. There are multiple ways of implementing this, but we're going to look at 3 of them. So one of them is how you do this in a very popular framework that is NodeJS. And then try to see how another system solves those problems. This system is called Swagger. And finally, we're going to look at Servant, which again solves a number of issues that Swagger introduces itself. And to be clear, the issue that we want to address is that there is a very tight coupling between the way we expose an API on a server and what the server does. In particular, what we do in practice is that we send publicly a documentation file that exposes all the endpoints that a client can access. And then implementations call those endpoints to use the server to their advantage. So, for example, a web page call the endpoints of the server that a web page calls the endpoints that it uses as a server to serve the pages. And so you might do something like log this user in, or get the list of items that this user requested, or add this item to their wish list. The first one, NodeJS, it looks like this. I don't expect you to understand every single line of code, but I want to pull your attention towards a very particular pattern that we can see here. Each part of the server is composed of three very similar elements. So the first part is parsing the URL. So we implement the server by giving it a request and giving it an opportunity to reply. And the request has the URL that we then parse manually. Here the parsing is just an equality check. We check if the URL is just slash, at which point it means that the URL is requesting the endpoint that is at the root. Or we check that it's slash student, at which point we infer that it is trying to access the resource that is at slash student, or slash admin, etc. After the parsing, we send a response, and every time the response is very similar, the code is the same in the three branches. So we say that the response, the request is accepted with a code. We give the type of the object that we're returning, and then we send response. And the final part is the data that we're returning, which type is said in the content type. We simply pass it to the response. So there is those three parts, which is parse the URL, send a response, and through this response, send some sort of output. Now this comes with a number of problems. The first one is that if we want to extract the API out of this program, we have to do some very careful control flow analysis to understand what the parsing functions do, and then infer from that a list of endpoints that a client can call, which is extremely difficult to do given any arbitrary program. What we would like to do instead is enforce that the advertised endpoint is indeed implemented by the server, or vice versa. Implement a server and then derive an endpoint from it, but in a way that is a lot easier by returning an object, for example, rather than trying to infer what is going on in the code by doing control flow analysis. And so this is error prone because now we can change the API by changing some piece of code that changes the parsing, or we can simply forget to return a response in one case, or return the wrong content type for the wrong kind of data, or simply just return the wrong data. And because there is no relationship between what the API is advertising, what the implementation is doing, we can't verify that those things remain in sync. And finally, because the endpoints are a consequence of the control flow of the program, there is no way to program them by saying something like create a new endpoint, create a new server with those endpoints, or create this new piece of functionality out of this existing piece of functionality. So from those issues, we're going to look at Swagger, which is another way to implement server and endpoints. Again, I don't expect you to understand everything that's going on here. What I want to draw your attention to is this center file here that describes the API. So here we describe an API by using a file and saying each endpoint look like this. They have those descriptions, they take those arguments, they return those responses. And because this file is well structured, we can use it to, as you can see on the right, derive some information from it, in particular documentation. And here we see an endpoint called device, and it has a get and a post endpoint. And we can have description for them and tell very easily what they do. But in addition to this, we also have options to derive implementation from them. So if we are given a list of endpoints as a server, we can derive code for clients that will call this server. So for example, again, a web page will use JavaScript to make a call to the server and say, please serve me the next page or the next piece of widget that I need to display. But you can also extract server implementation that say, given this list of endpoints, I want to create a stub or a server that would serve those pages or serve those endpoints. But again, this comes with a couple of trade-offs. The main one is that we add a new level of interaction when we are editing our server. Now, if you want to edit what the server does, not only you have to look at the business logic, but if you want to change something in the API, you have to change this original file and then generate new stubs and then copy paste those stubs into your code and then compile your code to ensure that the API has remained or that the API is compatible with your changes. And that is very tedious and error prone. The second one is because now the source of truth is split between the program and the API description. Those can go out of sync, and you need some additional infrastructure here to ensure that they remain in sync. So some sort of CI process has to do this automatic generation of the stubs and then compiling and then testing, etc. And so when you do a server updates and you want to diff what is the difference between two things, you have two files to look at. You have the Swagger file and you have the server implementation. And finally, because this file is purely descriptive, you can't program endpoints either. You can't generate endpoints as you want. So for this to be solved, we're going to look at Haskell and its server library servant. In servant, you define your API as a type. So here at the top, we have an API composed of 3 endpoints. And those endpoints are /position and then takes 2 arguments and returns a position, /hello, and then it takes a query parameter, which is a name and a string. And then final endpoint, which is /marketing, and then takes a request body from the request and returns an email. And what servant does is that given a description of an API as a type, it forces the server developer to provide implementation for each one of those endpoints. The first endpoint will be implemented by the function position, the second endpoint will be implemented by the function hello, and the last endpoint will be implemented by the function marketing, which are defined just below. And as you can see, the type of those functions are derived directly from the API here. So this comes with a number of benefits. The API and the code are always in sync because if you change the API, the type of the function that implements it will change, and so you get a compile error immediately rather than having to go through this indirect process with Swagger of generating a new file and then copy pasting generated code, etc. API and documentation is also always in sync because the documentation is extracted from the API definition. So you don't have to go through the implementation of the server to extract the documentation. You can simply look at the API definition. And finally, what solves both problems that we've seen before is that everything lives in the same language. The type is a type in Haskell and the implementation is a Haskell function. And both of them are 2 different objects in their own right that you can look at and manipulate. So if we recap, we have 3 kind of properties is Is our API in sync with the implementation? Is the API in sync with its documentation? And is the API easy to extend without breaking either of those? And so for Node.js, the API is in sync with the implementation, but that's kind of trivial, or that's not quite in the way that we want, because the API falls from the implementation. So they can never be out of sync, but you can really ensure what the API is to begin with. So this is a bit, this is a check mark, but it's not the kind of check mark that we want. And we can't extract documentation because that would need a lot of knowledge from the control flow and the implementation of the program. And it's not easy to extend because all of those can go out of sync without notice. For Swagger, the implementation and the documentation are always in sync because they both come from the same source, which is the Swagger file. But it's harder to extend because now if you want to change your implementation, you have to go through this additional step of changing a file that is outside of your source code and then generating more code, and then ensuring that this generated code matches your implementation. And this last point is solved by Servant, which ensures that the implementation and the documentation are both in sync, and every change you make is tracked and results in type error if you make an incompatible change. Which leads us to the question is Servant completely flawless? Because we seem to have gone through 15 minutes of advertisement for Servant. And there is indeed a number of things we can improve upon Servant. The first one is a consequence of the fact that APIs are kinds rather than data types, which means they are just types. In this following snippet, there is a mistake, but this mistake does not result in a compile error. This is a valid program, or rather this is a valid type, but this is not a valid API. The reason for this is that the greater than symbol allows you to compose paths, but it takes a type on the left and type on the right and doesn't really care what they mean. And well, not surprisingly, it's the same behavior for the arrow. The arrow takes a type on the left and a type on the right, and any type works. But this is not an API. This is a function between two APIs, right? We've put arrow here instead of greater than. This leads into a valid kind, but not a valid API, because API is not a function, right? And you see that you eventually get a type error when you try to implement this server, because the type families try to resolve this, but they can't because, of course, there is no path for functions, right? There is only, it can only resolve APIs, but the error that GHC tells us doesn't really help in figuring out where exactly the problem is. Indeed, because the problem is not in the implementation, the problem is in this declaration. So what we want is to find a way to constrict those kind operators to only paths and things that make sense. So composition of paths or branching of paths. And the other point is that because types are not first class, they're just kinds, you can't really manipulate them as a first class construct. So you can't really compare two APIs because it would be like pattern matching on two types. You can't really generate those APIs at runtime, which means you can't have a server that spawns new servers or spawns new APIs. And you can't well, that's the last point. You can't compose those servers together. So if you have a server implementation, you can't just say, I have this endpoints. Let me tack on more endpoints at the end of it because some new requirement came in and we need to do that. And so this is what we aim to solve by using both Idris 2 and lenses, or by using dependent types and lenses. Now we're going to shift into a more theoretical question, and that is, what is a lens? A lens is a construct of two functions. One that goes from a lens is a data type that is parameterized over 4 arguments, st, a, and b. And this data type carries two functions, one from S to A and one from S and B to T. And the original use case for this is to use lenses as record accessors. So a lens for a record can allow you to see the fields of type A for a record S, and it allows you to update a record S into a record T by providing a value B. The other way I like to think about this is as a system from which you can observe information, and if you poke it, you can transform it. So the S to A function is the one that will allow you to observe the state of a system, and the SBT function is the one that will allow you to poke the system and feed it a B, and then have it spontaneously transform into something else. And the neat thing about lenses is that you can compose them together. You can stitch them together into bigger lenses. So this composes a lens STAB and ABXY into a lens STXY. And the way it does it is simply by passing along the view to the next lens and saying, if I have an S, I can look at a T through the fact that you can see an A. And if I have an S and a Y, I can obtain a T by changing this internal lens into a B and then using this as argument for the first lens. So it's like a system deferring its behavior to a subsystem. And this is what we're going to use to compose multiple servers and views together. So as a reference, here's the Idris implementation of a lens. You see it's fairly straightforward. It's a record of 4 type arguments, and it has 2 fields, the function get from S to A and the function set from S and B to T. Another question is, how can we see a server as a lens? Here's an example of 2 endpoints, a server that exposes 2 endpoints. The first one is a endpoint that will accept GET requests, and it takes a parameter which is a user ID and the path to-do/all. And if we write the type for this endpoint, we see that it behaves like a function from user to list of to-dos. So if we provide it a user, which is the user here, the server will provide us with a list of to-do items. And similarly for the post request, if we send a request with method post to the path to-do/new, and the request body contains a new to-do item, we will be provided with a new list of to-do items for the given user. But this manifests in a return type that is unit because the action simply changed some sort of internal state. So we give it a user, we give it a new to-do item for this user, and we wait for the server to say, I've done my job, you can keep on going. And if we put those definitions side by side, and we remember what a lens is. So a lens is a data type parameterized over STAB, which has those 2 fields. We see that the get function looks like the get function from lenses, where S is our user and A is the value that we are expecting the server to return. And the update, the post request, takes the same user, and it takes our to-do item and returns a result. And S, we see, is the same for both requests. B is the new data that you insert into the state or the server. And finally, T is the result here, unit. You've probably noticed that I've mentioned state, and that is because the server has an internal state that we cannot see here. And if you were to attempt to implement a server using those type signatures, you will realize that it is indeed impossible to non-trivially implement the server, because given a user ID, you have no way to look up which user has this to-do list. You would either have to work in some sort of state monad or be given a state that you can look into. And similarly here, you need to look at what is the current state for the user, then update its state given the new value, and then return a reply if everything has happened as planned. So there is a bunch of state management that we haven't mentioned. So we need to amend our statement that this says that a server behaves like a lens from the point of view of the client, but the server itself might not be. So let's look again at our example and how we can maybe reintroduce this concept of state in our lenses so that we can also implement our server as lens and not only display a lensified API. So the crucial observation is that GET requests simply query the state and POST requests update this, just like lenses. But we also need to pass in the state that we're querying and updating, right? And if we simply add the state as an extra argument here, this looks a lot more doable, right? So in the GET case, we are given a user, we're given a state, and then we can probably extract the list from this user by looking at the state. And similarly here, for the POST request, we can, given a user and a to-do item, look at the state and change it, and then return a new state. And all of this is predicated upon the idea that when we update, we take our state and then we change it. And when we get the state, we don't have to change anything. We can just look at it, which is why this does not, the first one does not return a state. If we update our lens signature to incorporate this idea of state, we end up with a lens that looks like this. So S is now an argument, well, the list of arguments for your endpoints and the internal state of the server, and then returns an output, which will be sent as a reply to the client. And the POST request is also a list of arguments provided by the request and the internal state, along with a new value that will be used to perform the update. And that results in a change of value. So in the case of updating the to-do list, we elected to return units, but we can also return, for example, the now updated list of to-do items, along with the new state of the server. And we can see that the basic structure of lenses has been preserved. S has just become a pair, and T has also become a pair. This is still a valid lens. It still goes from S to A, then S, B to T. We just have a little bit more structure to this. So here's the structure, is that given any lens and a state, you can transform it in a stateful server lens simply by adding the state as the second component of each pair of S and T. Those are the functions that you would have to implement if you were to see a server as a lens, given those two endpoints. So the GET request will take a user as first argument, and the state will be some sort of hash map between user IDs and their assigned list of to-do items. And this will look up the user and return the list of to-do. I see this, this should say list of to-do instead of to-do. And for the set, we'll take an additional argument, which is the new to-do item to add, and insert into this list the item that has been given for the given user if we find it. And we return the updated hash map as the second argument. And the server library will take care of updating the state correctly for you and returning the response. So with that said, I would like now to show a demonstration of how this works. So here we have the server itself. All right. The first thing I want to show is that as a sanity check, we can recover. As a sanity check, I want to show that we can recover the features from servant. So if we compile this, we see that just like servant, we can define our server by giving it an API that is path components and arguments. So here the example is a bit simpler. We have the component boiler and lights, and this is an endpoint that returns a Boolean and accepts GET requests. And this endpoint returns also a Boolean and accepts POST requests with a body that contains a Boolean. And similarly for this one returns lights if we call it with a GET request. And we also return lights if we provide it a POST request with lights in its body. And as you can see, we can implement the server using the lens operations that we mentioned. The first one takes the internal state of the server and use gets to see it, get a focus on it, and set to update it. And similarly for lights. And the internal state of the server is written here. It is home states. And home state is simply a record that contains two fields, one for the boilers and one for lights. And lights is simply a triple of double values, which represent the intensity of the lights for each room in the house. This is very familiar if you're used to Haskell. And the way you instantiate the server is you give it an initial state, you give it the API to implement, and you give an implementation for the given API, and you simply run it in this main function. So if we compile this, we can now send requests to our server. So we're going to say get the status of the boiler, and we see that the response is false. The boiler is not running. And now we can do post boiler true. And so this post boiler true says send a post request to the boiler endpoint with the body true. And we see that the response is true. And we've also updated the internal state so that the boiler is now in the true state. And if you do get boiler, our response is now true. So server updates work fine. So we've managed to already achieve something here, and that is implement this basic API in terms of lens operations. Now the question is, how far can we take this idea? So one thing we can do is, instead of having two separate parts to the server definition, we can merge those two. We can say a server is both its API and its implementation, so that the implementation is in line with the API. You can't separate them. They're both one and the same. Which is already something that servants cannot do, because that would mean you have the API here. You have to pair up the API as a kind. Well, you have to have the API as a value, but since kinds are not values, you can't pair them up with other values. You would have to have the implementation as a kind too, but then you have to derive the function from the kind. That would be Haskell. So here we're doing the same thing. I've dropped the lights for the purpose of the example. We're doing the same thing. We're just saying we have the endpoint boiler. It's a GET request. Returns a bool. It works in the home state, and it's implemented by the GET part of the boiler lens. Similarly for set. I'm not going to compile. Well, I'm going to compile this. I'm going to show you that it actually works. So if I do get, I'm just going to directly post boiler true. We get a response that is true. Then get boiler. Okay, true, right? Initial state was false. So this does work. So we've saved ourselves one step. We saved ourselves the fact that we have to separately implement the server and the API. The next example simply shows that we haven't lost anything by doing this. So you can refactor your API by saying, instead of saying boiler in front of each endpoint, you can refactor it in a common prefix, and they say the common prefix is followed by those two endpoints. I'm not going to show this because it trivially works. It's literally the same as before. However, we can go one step further because those are simply values, right? We can extract this pattern of saying you have two endpoints. One of them is get, the other one is post, and both of them are implemented by the same lens, except one is the view and one is the update. If we abstract this pattern, we've implemented the entire server with this one line, which is our endpoint is this resource, which is defined by this lens, and it has this prefix in front of it. And it works in this state. And if I compile this, I do get boiler, false, post, boiler, true, true, and then get boiler, I get true. So we've come a long way from Haskell already, where instead of implementing our API as 2 steps, we implement it as almost 0 steps, where we just give the lens and say, there we go, do your thing. Can we just remove all of this, right? And inline it here. Yes, we can. So now our server is literally just this one line. And that will work perfectly fine. So now that we've achieved this, we can probably already do everything that we set out to do. So now we can compute something on those endpoints. And specifically, we can extend them arbitrarily given more endpoints. So imagine you have a server that's already defined like this. You can define a new server from it by saying, take the existing server, which is this, and put it alongside another server, which is this, with another lens, and also put all of this new server in a new common prefix, which is /home, right? So we've just taken, this is the old server, this is a new server, and we put those two servers together and we put them in a common prefix, which is, and then we do this, compile, and then run. We do get boiler, which is the endpoint we had. Oh, sorry. Get home/boiler. We get false. We can also do get home/lights, and we get our lights. I want to attract your attention to the error messages. The error messages are, I found quite interesting. So this one says, expected 3 arguments got 1. This is because given the path home/lights that returns this thing, it expects 2 argument, and we've only gotten 1. So it expects a path of length 3, but we've only gotten a path of length 1. So that indicates that the home prefix was not present. We missed it. Indeed, we forgot about it here. All right. So now we can define servers by putting together 2 servers that have already been defined, or they don't have anything together. They don't really have anything to do with each other. They just have a common lens with them. Can we take this idea further? Can we extend an existing server? So one of the things we want to do is, actually let me show you this. If we want to update our lights, we have to update all 3 lights together, which is not ideal. So if I want to update the second light, I have to do this, right? Something didn't work. Posts home/, oh, it's has an S. Home/lights, and then where's the value? And that worked, right? So now the second one is updated, but I don't want to overwrite the value of every light every time I want to change one light. So what I really want is one endpoint for each light. And thankfully for me, the light endpoints simply expose a triple. So in principle, it would be possible to extend this endpoint using the lenses that view and update the first argument, sorry, the first component of the triple, the lens that views and updates the second element of a triple, and a lens that views and updates the third element of a triple. This is exactly what the following example does. So we are given our servers again along with their implementation, and we're going to say extend the lights endpoint with a path that starts with kitchen, and its implementation is given by the first lens, which looks and updates the first element of a tuple. And similarly, for the second endpoint, which updates the living room lights, we're going to say this is given by the implementation of this lens, which itself, as you can see, is a composition of lenses. So this updates and views the second element of a pair, and this updates, views and updates the first element of a pair. So this says go to the second element of the triple, which is itself a pair, and then look at the first element. And finally, bathroom lights is the same thing as this, except we compose second lens with second lens. And this gives us our third endpoint. And then we can simply, this is an example for later. Let me store this. This was lights path. Now we can put together all our endpoints and instantiate this new server. And I'm going to quickly remove this. And we're going to say run the server with this initial state, and this should work. This. I should compile outside of here. Here. And now we run our server. So now we have get home/lights, right? But we also have get home/lights/kitchen, right? And that returns the correct endpoint, the correct value for the internal state rather. And now we can do post home/lights/kitchen and give it a value like 0.5. And you see that the state has been correctly updated to change the kitchen light. Similarly, like you can do post home/lights bathroom 0.7, and the third one is updated, and the previous state is maintained. Great, so I hope you can now see how this can be helpful. There's one more thing I want to show, and that is a question that will inevitably come, is that you always have to do get and post requests. What if you only want one of them? Because those are simple functions that abstract over the internal data type that defines paths, you can reuse any kind of other function. So this function here simply says this endpoint is nothing but a endpoint that take a get request and no post request, right? And implemented with the get function of the lens. So to show you this, I'm going to also show another example, which is just to make sure that we haven't lost any kind of functionality from Haskell. There is a small function here that generates documentation for a given server, right? So if we compile this, and we run it, this should just print the documentation. And you see we have generated a lot of endpoints in those couple lines. And in particular, I want to show you we haven't generated documentations for get lights, post lights. because we've said post lights only has a get request. The lights endpoint only has a get request, doesn't have a post request. And this, I think this is not very impressive if you're used to servants, but what I really want to show is the number, the amount of data that we have derived from those few lines. In particular, without writing any kind of implementation, only relying on those lenses, which you can derive automatically if necessary. And the last thing I want to show is if you were to re-implement this exact same endpoint in servants or in a servant-like program, I've reused the same DSL that I showed at the beginning, which simulates the same behavior as servant. So here you have your API. So you have the GPS for boilers, the GPS for lights, and then you have a nested endpoint for kitchen lights, living room lights, bathroom lights, etc. And then you have to implement every single one of them automatically, even though it turns out the implementation is extremely trivial and can indeed be derived automatically. So with this, we're reaching the end. I want to ensure that, I want to say that this is a huge work in progress. There is a lot of rough edges. There is a lot of things to do that aren't done yet. And it's nowhere near production ready. But the one thing I want you to take away from this is that there is a way to greatly improve and understand software, in particular server implementation, in a way that would make it a lot easier to write and specifically extend those pieces of software without introducing new errors or decreasing your level of confidence when implementing them. If we look at the to-do list, there is a bunch of things that need to be done that are not really related to the academical exercise. So the first thing is we need to implement HTTP requests, because as you've seen, I've been using the command line. I haven't been using curl. This is because the server simply waits for the command line to send it something and then sends it back on the command line. Morally, this is the same as listening on a socket and then sending things on a socket, but it just hasn't been done. I just need to spend the time to do it. There's a bunch of other things that simply require a lot of engineering effort. Generating client code would be nice, like generating JavaScript functions out of server API. The get only definition that I've shown has to be done manually. We can just write a function for this, and that's done. This does not support parameterized lenses, which means lenses that depend on an argument in the URL. So for example, if you say, get me the to-do list from this user, the lens would depend on the parameter that is the user. So there is no facilities for this, but there's no doubt that it can be done. This means, can we, instead of, currently we're giving the lens to derive both the type and the implementation of the server, but can we implement those lenses as interfaces or type classes, if you use to Haskell, and then have the compiler itself derive which lens should be used with which type, in which case you simply give the type of the server and the implementation follows from it. Because we're in a dependently typed setting, it is possible to have dependently typed APIs. For example, if you have an endpoint that paginates its results, you give me the next X lines of this list, you can expect the server to respond with a value of type vect of X of A, or whatever the item is. There is no facility for this right now, but there is no doubt that you can do it. In fact, there is a library that has done it. It's just another sort of engineering effort. Ensure that OPA is overlapping is also possible. The one thing that I think will require some theoretical effort in here is error management. So when you implement servers, you very often want to say that your API might return errors. So for example, your server might have a default fall through 404 for page not found if it cannot ingest any kind of request. Or if the request you've sent it cannot be answered. Or might display different kind of internal errors or authorization errors, etc. And you will, when you write this, you are very tempted to say, actually, the server returns this value that is the value that returned when everything goes fine, but also returns all those kind of errors in case something goes wrong. And there is no way to say this right now. But in particular, you might want to say, because those endpoints are implemented with lenses, you might want to say, well, those errors are prisms. Either I return this value, or I return one of those errors. And the return type is now a prism of the value and all the errors. And one thing that isn't here but should be here is deriving lens implementations and from a type. So currently all those, I've hidden all the implementation of the lenses because they're done manually. But you can and you should have a way to give a record and say, please derive all the lenses for this record. And similarly, you should be able to say, actually, this record has a special lens that works in this special way. I just haven't done it yet. In addition to the boring, not the boring, but in addition to the engineering task, there's a bunch of theoretical tasks that need to be answered. So this particular framework focuses on HTTP, which has a bunch of nice properties like get only views the state and never updates it, posts updates the states. You can say that puts and deletes also have their special form of updates, and then you want to expose them also as lenses in this regard. But can we use something else than HTTP, and what changes when you do this? So if you take something like a stateful protocol like UDP, where you can lose packets and you have state, you say, am I connected? Please connect me. I'm waiting for this. Can you send it to me, etc. Or Bluetooth, which is basically the same, where anything can happen. Can you still use this framework, and how would it change? In particular, if you can model the interaction using session types, can you include the type of the session that the server implements in its endpoint? So you say you have to be connected in this way to this endpoint. This would be extremely nice to do in Idris too, because it has linearity, and so you can have some form of session types. The next point is extremely important if we ever want this to be production ready, and that is to expose the server state as a database operation rather than as a internal state in memory. And it's not quite clear to me how to do this. I'm fairly confident we can have a limited version of this working, but I don't really know if we can have the entirety of SQL be represented as a lens, and how what would that mean for example, performance or composing SQL operations. But if you can do this, you can generally take this lens idea to production and then say, my server is a view for this database, and here are the endpoints that I will expose that will translate into those database operations. And now you have a very strongly typed object model, just like are very popular in dynamic languages, where the internal object model of the database is exposed through a type system and into your API endpoints. Difference being, now you have types everywhere, and you know when something breaks before you run tests or before you go into production. And additionally, because those, if you use dependent types, you might want to define types themselves as data types. This is the last point with containers and ornaments. You might want to define your states as containers and ornaments. and say, if whenever I do a database migration or whenever I add a new feature, what I really want to do is add an ornament to this data structure that will itself have either a migration path or a trivial conversion from one to the other that exposes this endpoint. And then you can track in the type system changes that are breaking or changes that have a migration path that you can implement. Finally, yeah, I jumped to the last one already. So the question is, how can we understand servers now in terms of what they mean formally? Can we see, for example, a server and its lenses as a containers and say, can we see a server as some sort of container and the lenses as some sort of morphism, and say a server that defers its state into this other state simply is a morphism between those two containers? And then similarly, some form of interaction model where we say any kind of requests that goes into the server is some form of endofunctor into this category of containers and functors, containers and lenses. And we simply go from one container as the current state to another one. This would allow an extremely powerful abstraction in which you can model both server communication and database communication and string together not only endpoints, but different parts of different programs as they communicate between each other. But again, this is not clear to me how it would actually work in practice. And it's even more far-fetched if you can actually implement this today in independently typed language in a way that is both ergonomic, practical, and performant. So I'd like to thank you for your attention, and I hope you enjoyed this presentation on optics for servers. And if you have any feedback, please tell me. And if you want to participate, this project is available on GitLab, and hope you will get something from it. Thank you.